This is part 4 of a series about the strong possibility of life on other worlds of our solar system. In this video, we'll be looking at the two most likely planets, Mars and Venus. Mars may be the most likely candidate in the whole solar system. Keep watching to find out why. For hundreds of years, scientists and science fiction writers have focused on Mars hosting life. 17th century astronomers discovered certain similarities between Mars and Earth. Both have polar ice caps. Although Mars is carbon dioxide, they look like water ice. Both have 24-hour days. The tilts of their axes are similar. Earth 23.5 degrees, Mars 25 degrees, meaning similar seasons. Mars also has dark patches which suggested oceans to some people. Based on what those scientists could learn with the equipment available, the idea that life might be present wasn't unreasonable. Starting around 1877, a few astronomers thought they saw linear features on Mars. These were interpreted as planet-wide water-carrying canals and the product of a high-technology civilization. This led to the 1887 publication of The War of the Worlds, the first novel about interplanetary conflict. Few of the ideas of that time were accurate. Actually, Mars is very cold and dry. The canals turned out to be an optical illusion caused by the combination of poor quality telescopes and overactive imaginations. Martian daytime temperatures of around -50 to -60 degrees would feel like an Antarctic winter. Martian nights get down to -140 degrees, making even Earth's extremes seem mild. Of course, this temperature range is far below the freezing point of water. More importantly, Mars's thin, low-pressure atmosphere means that the water can't exist as liquid there at all. Under those conditions, any water ice on the surface would evaporate directly to gas without passing through a liquid stage. On Earth, solid carbon dioxide does the same thing. That's why it's called dry ice. The Martian surface is also unfriendly to life. The atmosphere offers no protection against space radiation, so the surface is 100 times more radioactive than Earth. Not even the toughest microbes could survive that for long. Plus, the soil is highly oxidizing. Often we talk about oxidization to mean burning, but it also means to break apart large molecules. Not surprisingly, given the name, oxygen compounds are good oxidizers. The Martian soil contains a lot of iron oxide, which we know as rust. That's why it's the red planet. The substance would break down organic molecules. Yet billions of years ago, everything was different. For starters, Mars was wet. It had rivers and lakes, plus an ocean that covered up to 3/4 of the planet. Mars's surface tells the story. We have identified more than 150 Martian geographic features associated with running water. Many look like what on Earth are flood channels, although it would have taken a lot of water to produce channels as large as seen on Mars. At a place on Mars called Yellowknife Bay, the Curiosity rover, a cart-shaped space robot, collected samples of a type of clay that on Earth indicates floodplains and heavy rain. Other minerals collected from there suggest the hot, wet conditions typical of hydrothermal vents. That fits because Mars was also very volcanic. Again, we find evidence on the Martian surface. In 1971, the Mariner 9 spacecraft returned pictures of extinct volcanoes, the largest of which is roughly 600 kilometers wide and 21 kilometers high, plus a huge rift valley 4,000 kilometers long and 6 deep. Earth has rift valleys too. The planet's interior convection produces hotspots, where molten rock pushes up from below. If the hotspots occur under continental crust, the upward force raises the crust in a localized dome. Eventually, the crust splits in a distinctive three-armed pattern. However, Mars's volcanic features are far larger than any on Earth. Even when Mars was at its most volcanic, its crust was too thick to move as Earth's does. So the volcanic features stayed in place, getting bigger and bigger. Also, Mars's gravity is less than Earth's, so mountains can grow to a greater height. Billions of years ago, Mars even had white clouds, a somewhat more bluish sky, and an atmosphere 3 times thicker than Earth's today. Earth and Mars were pretty similar. In fact, Earth and Mars shared all the features that made life possible on Earth, particularly hydrothermal vents. This similarity lasted for perhaps a billion years. Since chemical reactions always happen the same way under the same conditions, and since Martian conditions were just like Earth's, then life must have evolved on Mars the same way it did on Earth. Martian life would also have reached the same level of complexity as terrestrial forms of the same time. This means free-living microbes. Internal changes to Mars over time brought the similarity to an end. Earth and Mars took different paths. The changes explain the lost volcanism, atmosphere, and oceans. It's all connected. Mars is substantially smaller than Earth, so its interior cooled faster. Small things cool faster than big things. You can boil 2 pots on the stove, and the bigger one will always stay warmer longer. Earth's interior remains hot enough to maintain a liquid iron outer core, which circulates. The movement of an electrically conductive metal produces a magnetic field. The Earth's magnetic field is quite powerful and protects our atmosphere from the solar wind. That's a constant stream of energy and fast-moving ions from the Sun. Mars once had a magnetic field like Earth's, but lost it over millions of years as the outer core cooled and stopped circulating. While the Martian outer core is still quite warm, it's not runny enough to circulate as does Earth's. No core circulation means no magnetic field. Without that, the Martian atmosphere was exposed to the brunt of the solar wind. The atmosphere was basically blasted off into space, while at the same time Mars's weak gravity couldn't hold it. As the Martian atmosphere slowly blew away, the pressure became too low for liquid water. It evaporated. Or rather, not all of it. When Mars had an ocean, the top few kilometers of the crust would have been saturated with water, as is Earth's. Most of that subsurface water is still there, and Mars remains warm enough inside to keep it liquid. We know this because the Mars Global Surveyor spacecraft returned pictures of eroded gullies thought to have formed within the last million years, billions of years since the last surface water. Then, in 2011, the spacecraft detected dark streaks which had not been there in previous years. We have since seen that the streaks grow in spring and recede in winter, indicating a seasonal thaw cycle. Therefore, there must be salty water underground. During spring and summer, it seeps out into the surface and then evaporates. As we know, liquid water makes life possible. So, if life ever evolved on Mars, there's no reason to suppose that it couldn't still exist beneath the surface. 2 or more meters should be deep enough to protect from the radiation. Mars has enough leftover volcanism that it's also possible some underground hydrothermal vent systems may still exist. We know subsurface microbes on Earth can get everything they need directly from minerals without light or oxygen. Martian microbes could do the same. If so, that would explain a mystery concerning Mars. Methane escapes from underground in a seasonal cycle. Formaldehyde, a complex organic molecule, has been detected in the same cycle. Yet these compounds are not stable under Martian conditions and must be continually replenished. Although in both cases volcanic processes could be responsible, very active processes in the case of formaldehyde, Mars is no longer volcanic enough to account for the presence of these gases. The only other explanation is some kind of microbial life. Some would say that this idea has already been tested and discounted. Yet there's a new chapter to the story. The Viking 1 and 2 probes landed on Mars in July and August of 1976. Both carried the same equipment called the labeled release experiment, designed to look for life. The instruments gathered Martian soil, warmed it up and added water, then waited to see what happened. The samples released carbon dioxide. Taken alone, this would have been definitive proof of life on Mars. Unfortunately, the experimental controls to which water was not added gave the same results. This, plus the lack of organic compounds in the Martian soil, has been interpreted to mean that the released gas had a non-living origin. Scientists also thought that the ultraviolet radiation from the sun would be too high for life. That, plus the dryness, plus the oxidizing environment, all meant that the Martian soil should be incompatible with biological processes. That was a big hit to the idea of Martian life. 20 years later, scientists got their hopes up again. Then they publicized a Martian meteorite named ALH 84001, discovered in 1984 in Antarctica, which supposedly contained evidence of fossil cells. It may seem surprising that anything Martian could be found on Earth, and that scientists could be so sure that the rock is from there. Nevertheless, chemical and mineral analyses indicate that it's true. Yet the rock's initially convincing features eventually turned out to have a non-living explanation. Again, the scientific community was disappointed. It's often difficult to prove microbial origins of mineral structures. Some non-living processes can produce similar-looking results. Nevertheless, the present non-biological interpretation of ALH 84001 doesn't explain the presence of the mineral magnetite, often associated with life. Furthermore, the possibility of a biological connection to certain minerals keeps coming up in other contexts. For example, a group of scientists argued in 2016 that cauliflower-shaped silica formations found on Mars in 2007 are similar to structures found in the Atacama Desert in Peru, which themselves strongly resemble those found in volcanic parts of Yellowstone National Park in Wyoming, USA, and believed to have a microbial origin. Adding to the recent optimism, the original non-living interpretation of the labeled release experiment has been thrown out. Rafael Navarro Gonzalez and his team argued that the Martian soil oxidants would have destroyed any organic molecules during the labeled release heating stage before analysis. In 2010, they confirmed that a compound called perchlorate, discovered on Mars in 2008, destroys organic compounds when heated. This means that the Martian soil may well have organic molecules after all, although our experiments may have destroyed them in the samples, since a major reason for the non-biological interpretation of the Viking results has been removed. The question is again wide open. In any case, underground extremophiles were unknown in the 1970s. If they had been known, the mission might have looked under the surface. Coming missions certainly will. Venus comes closer to Earth than any astronomical body except our Moon. Visible with the naked eye at either sunrise or sunset, Venus looks like a very bright star near the Sun. Hence, we've known about Venus throughout all history. For centuries, astronomers have very precisely known certain features of Venus, such as its exact orbit in relation to the Sun. Yet Venus is very difficult to study from Earth. Venus appears almost featureless, even through telescopes. Except for the discovery of its atmosphere in 1761, little else could be learned about Venus until the 20th century. The first serious scientific speculation about life there started around 1870. Initial ideas involved Venus being hot, since it's close to the Sun, yet habitable at the poles. After World War I, scientists started thinking of Venus as a swampy world, similar to Earth as it was during the Carboniferous period 360 to 300 million years ago. Again, reality turned out very differently from the speculation. In 1939, scientists first described Venus's greenhouse effect and introduced this concept. A greenhouse is an all-glass room for growing plants in a controlled environment. Energy from the sun enters through the glass but cannot escape, thereby warming the room's interior. Even on a freezing winter's day, a greenhouse can be balmy inside. Planetary greenhouse effects are similar, except that the atmosphere fulfills the role of the glass. The principle affects many worlds with thick atmospheres, including Earth. It means that these worlds are warmer than they otherwise would be at a given distance from the Sun. Greenhouse calculations for Venus indicated that the temperatures should be far above Earth's. In 1962, the Venera 1 lander confirmed Venus was an inferno. The surface averages 450 degrees, way hotter than your home oven, and hot enough to melt lead. Atmospheric pressure is 90 times that of Earth's at sea level. In other words, the Venusian surface pressure is equal to the pressure on Earth 900 meters underwater. At those pressures, an unprotected human body would be crushed in seconds. Today, we also know that the Venusian atmosphere is mostly carbon dioxide, the gas used in fire extinguishers, with clouds of sulfuric acid. The surface has no water at all. That doesn't sound very friendly to life, so why are we considering the possibility of life being there? The answer is that Venus was once even more Earth-like than Mars, because Venus is nearly the same size as Earth. However, it too changed drastically, although in the opposite direction to Mars. When we say Earth-like, that means like Earth of 4 billion years ago and not like the Earth of today. Earth then wouldn't have been pleasant. For one thing, you would have needed breathing equipment because of the carbon dioxide atmosphere. Also, the air would have appeared constantly foggy because of the hydrocarbon smog. Life itself is the major reason Earth is not like that now. Life liberates oxygen, which cleans the air. 4 billion years ago, Venus would have been a lot cooler. The Sun was 30% less bright than today. We know that because helium gradually builds up in the core of the Sun and similar stars as a product of fusion. These stars are too small to have enough gravity to fuse helium, so the helium sits in the Sun's core doing nothing. A mature star finally balances two powerful forces, the inward pull of gravity and the outward force released by fusion. Helium in the Sun's core contributes nothing to the outward force, yet adds to the star's gravitational pull. As helium builds up, the balance of forces slightly favors gravity. Over time, gravity squeezes the star a little bit harder, dialing up the fusion a bit. So stars steadily increase in brightness. Our Sun gets 1% brighter every 110 million years. Thus, 4 billion years ago, Venus was in the so-called habitable zone around the Sun, where water can exist as surface liquid. Then, Venus was only a little warmer than Earth today. Although its 60 to 80 degrees would have been unsurvivable for us, these temperatures would have been well within the tolerance of Earth's earliest forms of life. Venus's present atmosphere retains evidence of its previous composition. Today, it has very little water, but the ratio of hydrogen to deuterium tells us that the atmosphere once contained at least 150 times the present amount of water. From that, we can work out how much must have been on the surface, enough for an ocean. Some scientists say the ocean lasted 1 billion years, others say 2 billion. Either way, it would have lasted long enough for life to have evolved as on Earth. Whether or not it had an ocean, Venus was definitely highly volcanic and still is. This combination makes it very likely that Venus had the same kind of hydrothermal vents that incubated terrestrial life. Venus consists of most of the same minerals that make up the Earth, meaning that Venus's ocean, if it had one, would have been chemically enriched as on Earth. So Venus, like Mars, may have duplicated all the same conditions that led to life on our world. What happened to Venus? The answer is a runaway greenhouse effect. Venus, Mars and Earth all certainly had large amounts of water in their atmospheres. Water vapor is actually a greenhouse gas, although it also removes carbon dioxide, a far worse greenhouse gas, from the atmosphere. On Earth, carbon dioxide dissolves in the oceans. Carbon is deposited as carbonate rock, which is eventually buried underground by plate tectonics. These processes gradually remove carbon dioxide from the air. Although Venus and Earth are very similar geologically, Venus has a thicker crust. Therefore, it never developed plate tectonics as did the Earth. That requires a thin crust. If Venus and Earth are so similar, why did Earth develop plate tectonics but Venus not? Textbooks conventionally explain that the reason concerns water. Water weakens below crust rocks, making them flexible, while also reducing the friction affecting plates. Dry, stiff rocks can neither break up into plates nor slide past each other. Yet perhaps this theory doesn't fully explain Venus because it had plenty of water and for long enough. A more important reason is that a good part of Earth's former crust is now orbiting above us. It's the Moon, formed as a result of an impact with a Mars-sized body that nearly destroyed the Earth. What remained of Earth's crust after that was much thinner and pliable. Venus never experienced such an impact, so its crust remained thick and it never developed plate tectonics. Without that, Venus was never going to be able to bury carbon dioxide as the Earth does. As the Sun's luminosity increased, Venus warmed. Water evaporated from the oceans into the atmosphere, adding to the greenhouse effect. The rising temperatures also released carbon dioxide from rocks into the atmosphere, warming the planet still further. Eventually, it became too hot for liquid water. The oceans boiled off. With no water left to remove carbon dioxide, the planet entered a positive feedback cycle. The warmer it became, the more carbon dioxide was baked out of the rocks, making the planet still warmer. By the way, the Earth will go through something similar about 1 billion years from now. Yet it's possible that Venusian life, if it evolved, retreated underground the same way Martian microbes could have. Venus doesn't have plate tectonics, but it may have a different kind of tectonics. The idea is that every few 100 million years, interior heat builds up to the point where the entire crust melts and then resolidifies. This is still unconfirmed. If Venus does have that kind of tectonics, there is zero chance of life surviving. The two key questions for Venus are, what kind of tectonics does it have, and are the subsurface rocks wet? Depending on those answers, Venus may have a thriving underground community. Some also say that life may yet survive at high altitude in Venus's atmosphere, above most of the heat. Time will tell whether they are right. In spite of Venus's closeness to Earth, it is one of the most difficult planets to study on the ground. To date, no lander has survived more than 2 hours of surface conditions. It may be a long time before we can put a rover onto the surface of that world. If you'd like to learn more about this topic, click on the next video. That's about the ice moons. The solar system has many of those, but Europa, Enceladus and Titan are the most likely to host life. Thanks for watching.